Yeah, I think we're ready to start here. Okay. Um, so just a quick announcement. I posted this on the board, but next week I've got to be out of town the whole week. So since it's a high flex class, we're just going to flex to the online version of it. So we won't have in-class meetings next week. The class will run virtually the same. We'll still have discussions, postings, an explore activity and the learning activity. In fact, all that I think is live right now and available. We just won't be meeting in class. If you get stuck in stuff, I will be available online or in by email or phone. Probably mainly in the evenings when I get access to Wi-Fi for things. So um, on a keep meeting, I'll try to post also. We've got two TAs, Eba and Allie, who can help with this. So if you're getting stuck, I'll try to post for next week access. They'll be on campus. And so if you want to do that, they're listed in the course already, and they've been helping with some of the scoring and stuff. But they'll be, as we get into more complicated stuff, they'll be available for any sort of help, tutoring sessions, helping you walk through an assignment or stuff. So I'll post an announcement with their contact information. I think they have a spot where you can sign up for a tutor session or something like that, or just email them also. So I'll try to post that early next week while I'm out of town so you can see that. So today is Thursday. So, and let's jump back to unit 3. We're doing unit 3 here. And we'll be walking through this learning notebook here. Basically, we're going to look at these different classical classification algorithms and apply it to the iris data stuff. So that's kind of normal stuff. Open up the this learning practice notebook or stuff, and then you'll want to make a copy of that and open up the write-up and make a copy of that here, and then you'll want to be editing both of those here. And again, you can submit them either way. Some people have just been submitting a link to the learning notebook, and then that has a link to the write-up. Some people submit the write-up and has a link to the learning notebook. I grade largely from the write-up here. So mostly the one I want to see the most is the write-up. So if you want to submit a link, you can submit a link to the write-up, or again, you could download it as a PDF. You're fine to submit it that way too. I'm not too concerned. I know some fact they're concerned about, students fudging the deadline when things are due by submitting a link to an incomplete document and then going to the document and finishing up after the deadline. I don't care if you do that or not. So if you want to just submit a document and stuff, a link to the document, or if you want to download it as like a PDF and submit that, that's fine too here. So again, we'll be doing these two activities here today and walking through those here. And again, this is just normal kind of classification problem. And we've talked a little bit about this iris data because again, remember there are 3 different types of iris flowers. We have about, and we have data, the sepal length, the sepal width, the petal length, and the petal width for these datas, and we're trying to work with that here. And we're going to work with a number of classification algorithms. Today, we're mainly working with k-nearest neighbor, support vector machines, and decision trees. And then we'll look at some ways of combining those together for this. There are lots of different classification algorithms. Scikit-learn, which is the library we use, has a number of them here: nearest neighbor, linear support vector machines, RBF, these curved support vector machines, decision trees, Gaussian random forest neural networks, and some boosting stuff they have. And so they have information on that. But again, we're just going to focus largely on these three here. So anyway, bring in IRSOS. So we're importing our libraries here. And again, you'll notice that now we're importing a lot of this sklearn, this scikit-learn stuff. And that gives us access to like the decision trees, the k-nearest neighbor classifiers, and then also this training test split, which we'll see in just a sec, and a scalar here we'll talk about in the project. Then we're going to read in the iris data. And again, this is a quick display of it that had. And again, we're going to break the data up into X and Y components. The input is the X, and that's going to be the four numbers. And the output is the Y, and that's the category, the species. So the Y is just that. So we're going to do that split. And again, remember we talked about like using iLock to grab certain columns or certain rows? That's what we're doing here. And again, there's different ways of doing it. So here we're grabbing the first four columns and making that X, and then the final column, and we're making that Y here. And again, I'll generally provide this code for you. And again, if you are interested in this code, you can look through and explain it. You can actually have Gemini explain this more to you. You can click on the Gemini button here and have Gemini explain this code to you. But again, this isn't a Python programming course, so I'll generally have this set up for you here. Then we're going to, again, split the data into parts here with this. And so we're going to do 80% of the data for training and reserve 10% of it for testing. So 10% of the flowers we're going to set aside, and we're going to train or set up the whole model and train the model. And then without ever seeing this test data before, they've seen it before, well, they'll then use this test data on the model, see how well it performed on this new data it's not seen before. So this is what this train test split is. And this is just, again, it's a library. It's part of the scikit-learn. You just say train test split. You specify your X and your Y, and then the size. And then this is a percent. 20% is going to be reserved for testing. So if I look at the shape of my data here, I get an idea. So I have 120 flowers for input, and each one has four numbers. And for the output, I have 120 flowers, and then there's just one output, the category. And then reserved for testing, 30 flowers are reserved for testing, and each one has four inputs. And for testing output, again, there's 30 flowers, the same 30 flowers reserved, and just one category. So that's what we're kind of looking at, just to get an idea. Make sure the train test split, or convince you that the train test split worked here. And again, here's our X, our flower data. And notice now, before we had the four numbers and the species as the final thing. Now we just have the four numbers and not the species here. Because again, that's what we're trying to predict. So we're going to try to give it this number and see if we can predict the species correctly. And so here's the Y, and that's just all the species, the Iris setosa or Iris virginica. So again, I've got that all set up and run. First thing we're going to do is k-nearest neighbor. Now, first I'm going to ask you some questions to see if you understand how this works. So again, let's say we're trying to classify apples and oranges by two different factors here, values here. And we have some marked as apples, we have some marked as oranges, and we have some new X value here. So this X value is, again, about what, not quite 18 and not quite 5 value here. And that. So if you look at your write-up, I think that's your first question. The classification of X said, I guess we're saying it's 18.8.4.9 when K equals 1. So again, if you look, you can look at it here also at where this X is, if you just look at the nearest neighbor, one nearest neighbor, what would you say that X is? Is it an apple or an orange? Here. Yeah, it's the nearest neighbor is orange there. So, and then again, if you looked at K3, the three nearest neighbors here, what would that be? So I'm seeing an orange, an apple, an apple. So there's more apples there. And again, if you looked at the five nearest neighbors, so you keep saying, what are the five nearest things? How would you classify it? Here. So just fill in that section of this. And then we're going to try and do it with the actual iris flower data here. So hopefully you can kind of see that. Now here's our code for doing the iris flower data. We create a model, and I'm just calling it KNN model. Give it a name. It's a K nearest neighbor model. And I specify how many neighbors here. So I'm going to switch this to a smaller. I'm going to say, let's do 3 neighbors. So I'm going to say K nearest neighbor, and the number of neighbors is 3. And then I'm going to run this there. We fit it to the training data. This goes to the training data and finds the, does some math so that sees how it kind of fits with the training data. And then we score it with the test data. So every value in the test data will supply it there and see how well it performs here. And then we print out the score. And the score is going to be a percentage. So if it's 1 or 100%, it gets them all right. If it's some other value, like if I look at lots of neighbors, it gets confused. If I do 100 neighbors, it's only 56% correct. So it only gets it right about, if I look at 100 nearest neighbors, it's only right about 56% of the time. Again, when we print off this result, you can interpret that as a number between 0 and 1, and that's the percent value of it. So that's not 0.5%, that's 56%. So your job is then to try out some different values here. So what is the value with 1 neighbor? So go into this code, set the number of neighbors to 1, and see what you get. And when I got it, I got a 1 here, 100%, or just a 1. Now, you will get different results here for different values. Why do we each get different results? Because up here, when we do the train test split, there are some hard, there's a bunch of easy flowers that classify, but there's a handful of hard flowers that classify. And if you get some of the hard flowers in the 20% test set, your scores will be lower. If you get if the test set ones are all pretty easy ones, you'll do better here. And that's why it's better to have a bigger data set so that we wouldn't have this, it would kind of neutralize or reduce this variance. But if I run this again, run my train test split, and I go down here and run this again, I might get a different value. So now I was getting 1, I was getting 0.96. So each of you will get slightly different numbers often here, depending on how which flowers you're training with and which flowers you have tested. And we only have 160 flowers. So, and again, there are about 6 kind of challenging flowers. And so depending on how that works. Now, if we had 100,000 or 10,000 flowers, then it wouldn't really matter so much which 1,000 we put into testing. But because this is a pretty small data set, you'll see some variance depending on that. So again, you try it with 1, note that in the write-up here. Try it with 3, 5, 20, 50, 100, and just put your scores in here. Each time just updating this value. So with 3, I'm getting that. With 100, I'm getting that. And again, it's printing off lots of digits. you can ignore, I mean, really, you just want to look at the first two digits. That's the only ones that are significant, probably in this case. And again, if you want to write that as, 56, I could write this as 0.56, or I could just write it at 56%. Either way is fine with me, how you write that. I don't know if you remember, but we talked about this pipeline, and this kind of, I'm going back to that here. Remember, we import our data, we then clean, scale, or normalize it. In this case, we're not doing any of that. We're saying our data is fine here. Then we're taking our data and we're breaking it up into X and Y. And again, so we're separating what we're predicting from what we're using as input. And then we're doing a train test split. We're setting some of the data for training, some of the data for testing. So we've set this data aside, we're training it or fitting the model. So we created this model and now we're testing it out with the test data. Well, once we have this model, we can also use it to predict things. So another thing we can do is prediction here. So let's say we had a flour measurement of like 5.2. We found a new flour. We got a little metric ruler out and we measured, the sepal is 5.2 centimeters. The sepal width is 3.3. The sepal length is 1.4. And the petal width is 0.2. So we can use that. So this is what we can use to predict. Once we have our model, our KNN model is what I named this one, we can say predict, and we can give it some flour measurements, and it'll generate a prediction for us here. So this is one that's doing, again, 4.23, 3.4, 1.2. If I run that, it's going to say that's an iris setosa for this. So it'll say, now it might give you a warning here. You can just ignore this warning. It's not important here. Just look at the prediction here. We could try this one. The top one was, and again, the order of these matters because it matches the order of our columns here. Sepal length, sepal width, petal length, petal width. So the order of our numbers is important here. So again, if we have sepal width of 5.2, sepal width of 3.3, a petal length of 1.4, and a petal width of 0.2, I can enter in some new values here, run this, and it'll tell me that's an iris setosa. So for your write-up, you have to do two predictions. Tell me what this one is and what this one is. I'm going to just talk a little bit about the project. Again, this is only unit 3, and the project's not due till next week. But this project's set up so that you could start it now. And in fact, it's very much related to what we're doing now. If I scroll down to the project, and again, the projects will be listed, the same projects listed both in unit 3 and 4, because it's a unit combined project here. And you have two choices. You can do credit card fraud, which is clustering, which uses a slightly different technique here. And this bonus activity to walk through clustering. We work with like how do we cluster things. But the breast cancer option is this one. So you can choose either path here. If you choose the breast cancer one, it's very similar to what we're doing now there. And so I'm just going to walk through parts of that as we're going through this stuff. So I'm going to bring up the Project 3 breast cancer stuff here. And again, it's looking at k-nearest neighbor, smart vector machine decision trees, and some of these ensemble methods that combine them here. We'll bring in our data here. And again, this is our breast cancer data that we've seen from the University of Washington. So it's 30, about 30 different values for this stuff. One thing to note is that with the iris data, the numbers are all kind of in the same range here. So if I look, like the sepal length goes 5, 6 values, and the petals are maybe 1, 2, 5. So there. And again, the petal width can be smaller. I mean, this is getting a little bit smaller, like 0.2 to 2 there. But they're all in the range of like 0 to 8 there. None of them are in the thousands, and none of them are like a fraction, 0.001 or something like that. They're all 4 of them are in the same range here. So we don't have to do what we call much scaling with this. When we look at the breast cancer data, though, we see different things. Like the radius is like 17, 20, those values, where like the area mean is like 1,300, 1,200. So that's a lot bigger. It's an order of 100 times bigger than this one here. And then if I look at some of these, like the smoothness is like 0.08 or 0.1. So again, that's about can be almost 100 times smaller than these. So some of these columns are 100 times bigger than other columns, and some of these, some of them are 100 times. So there's almost like a 10,000, a factor of about 10,000 between these things here. And so this is someplace where we will want to do some scaling of this data, and we'll talk about that. So in your write-up, we'll talk about that. But again, that's our data. We bring it in. We have to do some cleanup. So we'll do some cleanup on this data. And I actually have that set up for us here. The one thing you do have to decide is which columns you want to use for this data. With the iris data, we only had 4 columns. So we're going to use all 4. Here we have like 30 columns. So the question is, do we want to use all 30 for that? So you can, if you uncomment this line, it will set X to all 30 columns. Or if you want to just test out with only some columns, we can try some columns we think are good. And again, when they're doing research scientists often try to find, which of these measurements are worth taking to be useful. So they might try different combinations of columns and see how good the results are and say, oh, you know what, we get really good results if we only do these measurements. We don't have to do all 30. We can just do these 5 or 6 measurements and get as good a results. So part of your job in this project is to set X either to some featured columns or up here to all the columns for this and try out the results. And again, we do a train test split. We do an 80-20 split with this, and then we do our k-means. And look at this. This code looks very familiar to what we have when we did the k-means over here. It's basically the same code here. We create our model, and again, I just called it a K&N model. We fit it to the data, we scored it, and we printed off the results here. And again, you have to decide how many neighbors you want to try for this. Now we have a lot of data in here. How much data? I'm trying to remember how much data we have in this. I don't see. I think we have thousands of data points maybe in here. Okay, so. And then we try to scale the data. And again, this is what we don't have to do with the iris data, is scale it. And again, scaling is not hard. to do. You can import different types of scalars. We're just going to use the standard scalar. We just import the standard state data. We take X and we say fit and transform it to make a new X. And now this new X, all the values are kind of in the same range. It's kind of in the 0 to 1 range. I think it's actually with the standard scale, like about maybe negative 1.5 to positive 1.5 or something like that. But they're all scaled. All the values are, each column is scaled together. And then you can run this and see if you get better results with the scaled data than the not scaled data for this. And again, that'll be part of your project if you choose the cancer path for it. Okay, let's go back to the iris data and do sport vector machines here. So again, remember sort vector machines, we're going to try to find a good line here, and we're going to pick by default, to start with a straight line to separate our data here. And again, there's two kinds of kernels. Linear, it uses straight lines, and then there's RBF, radial basis functions, which will be more of a curved ones. We also will have a parameter for C that we have to specify for this. Here's a good overview from a stack site called Stack Overflow, talking about what C does here. And again, it's kind of showing you the penalty here for what things are. So if we have a line through here, and we can't find a line that keeps everything perfect. So like this one, if we draw this line, this one blue circle is going to be classified as a green X here because of the way this line is. And again, we can try to impose some penalties so we make sure everything tries to get classified correctly for this. So the higher the C parameter is, the more you're going to want to worry about some different value. Like here, we have all the blue ones over here, all the green ones over here. So we have one kind of stray one down here. If we don't have much penalty, we'll draw a nice line right here. So if C is relatively low, we'll draw this line right here. But if we don't, we want to make sure we get everything as good as we can. We have a penalty if we get one wrong, like a high penalty like 10, then we're going to draw this line differently. So we're going to draw this line over here so that we get everything. But that's can give us kind of a weird classification if we, if we get new data we haven't seen here. Okay, so now you're going to run this. Here's our code. Here we set up our sport vector machine, and again we specify two things. Here I'm going to go back and do this one, the linear one. I'm going to specify a C of 1, which is the default, basically an average value, and a kernel is going to be linear here. So I specify it, we call fit, and then we score it on the other one. So I can try this out here. And I get a pretty good result here. And again, this will depend, you'll get slightly different results depending on your train test split here. But again, I can try a higher penalty, a higher C value, and see if that reflects that. I can try a lower penalty, see how that affects this. Oops, I guess it can't be 0. Or I can try linear, and I can try a curved RBF kernel and try that. I'll just warn you, a lot of our results are going to be the same with this iris data because it's again a relatively small data set. So you often run this with different values of C and stuff, and with this one you probably won't see that much difference. Now, when you get to the project, like if you do the breast cancer project here, you'll be trying the same thing, and you will see different, more varied with the results. So if I change C here, I'll tend to see some changes in this score often with this. So just be aware when you're doing this, you might see a lot of the results the same. And just put those in your write-up. So support vector measuring, try a couple different combinations of stuff and note your scores. And again, your scores will be different than my scores here. Update that. One of the criticisms for both k-nearest neighbors and support vector machines is that there are parameters you have to set here. You have to set, how many k-nearest neighbors, what k, how many nearest neighbors, or for support vector machine, the C penalty and the kernel there. Now, that's one of the reasons why some people prefer decision trees, because there really aren't any parameters for decision trees here. So here's our data for a decision tree. We just created model, give it some name. I'm just calling it DT model here. We fit it to the data for this, and that'll calculate the decision tree, look through all the data and figure out that decision tree. And then we can score it and look at the results for this. So again, no parameters set, nothing. You just create a decision tree and run it, and that's what you get for this. It is kind of helpful sometimes to see what's nice about decision trees is you can see how it works. So there is a process where you can print out how this works. And so again, we're looking at petal width less than 0.75. And if it's so, it's a setosa. Otherwise, then we're going to, if we look at the petal width again, and if it's less than 1.65, we're going to go down this path. Otherwise, we're going to go down this path here. And then then we're going to look at the petal length. And then we're going to look at the sepal width and determine that stuff. One thing that is kind of interesting here is you can sometimes see that there might be measurements that aren't being used. So in this decision tree, we look at the petal width. We look at the petal width, petal length, petal length, petal width, sepal width here. But one of them isn't used here. So again, you can kind of see that maybe you don't actually need all 4 measurements here with this. So depending on how they do this classification. So again, in your write-up, you should note decision tree, what your results is. Again, there's not a whole lot we can ask about that decision tree. Next thing we want to do is put these together in a random forest. So with a random forest, we're going to tell it how many estimators, how many trees to generate, and it will then give each tree a random set of the training data for this, and we'll see the result. And in general, a random forest should give better results than a single tree, because again, this one is creating 10 different trees and combining them together to get a result here. So we get our result for that. Now we call this an ensemble activity because again, we're bringing together multiple ones. The random forest is just a bunch of trees. You can also do an ensemble with other things. And so that's what SIXG boost does. Extreme gradient boosting. So what that does is try to look at where there are problems and apply certain trees to certain problem areas, not just randomly here. And I'm not going to go into too much detail of how it does that here. I have trouble even explaining or understanding it all the time. And so, but again, we have this. We do have to do a little transforming of our data because this is a slightly different library than what sklearn uses here. But again, very similar. We create our model, we fit our model to our data here, and then we score the model on our results for this. And again, you don't have to specify the number of trees. It will use what it thinks is a good number of trees, depending on how your data is set up and where there are issues, for this stuff. But you can kind of envision this is like maybe you were trying to determine, like, for cancer here, if some tumor is cancerous or not. And so we'll start with our first physician and we'll ask our first physician. And for a lot of tumors, the physician will know, oh, that's cancerous, that's not. That's very clear, very clear. But maybe for like 10%, the doctors, I don't think that, I'm not sure, but I don't think that's cancerous. I think that is cancer. So we can often with these models, we don't talk about it, we can often say, well, we think it's this way, but this is how certain we are for this. And so in that case, then if there are some areas where we're a little uncertain, the first physician might not be 100%, say, well, in this case, I'm not quite sure. We'll get a second opinion. We'll bring in another opinion in those cases. And so that's what SK boosting is doing. It is actually using one decision tree and just setting everyone and then it's looking at where are we unsure or getting things wrong at, and then we're training another physician or another tree just on that subset of data where we're unclear of for that. So it does kind of something like that. So that's what you're doing with the XG boosting. We used to actually, it's nice. All this stuff is now built in. It used to be to do boosting, we had to write complex Python code because there weren't libraries for this. And this is what we'll see a lot is that things that are new, you have to program in all by code. So again, originally we'd have to do, the people who could program in this could win the competitions and stuff. And eventually it got so common that there are libraries and now we can do this XG boosting in the same way we do anything else there for this. And you might ask, well, if this works so well, why do we even learn the other ones? And again, a lot of people in businesses will not use anything other than this. This is they only use like a boosting model like this. They never even use support vector machines or decision trees by themselves. They always use one of these ensemble models. But again, I think it's important when you're first learning to know what the different models are and how they're kind of brought together here. And again, we'll see that later on, like when we get to more complex neural networks or large language models, the newest thing will be hard to do. And then, within a short amount of time, people will put this in the libraries and make it much more accessible to everyone else. Okay, let's talk about the last thing, processing these categorical inputs here. So this comes from this pet adoption prediction challenge in Kaggle. This is an old challenge from 2019, but I still like the data, and we can still submit things and do these results here. I'll just note that this is not data from the United States. Here's the data from Malaysia. So some of it will be different than other things that you're used to if you know are familiar with American um, pet adoption stuff here. Um, and again, we're just going to look at the data. They actually included things like the photo of the pet in here and the description of the pet. And we're trying to do things like, given the photo, can you figure out some cuteness meter based on the photo of this pet? And does that impact this? But we're just looking at the data itself here. Uh, and so we have things like the color, the maturity, the fur length, short, medium, long are not specified. Vaccinated, 1 is yes, 2 is no, 3 is not sure here. The health, healthy, minor injury, serious injury is not specified. So we have all this data. And so we're going to try to take that data. And so here's a subset of that data in this table here. And your job is to figure out what of it is numeric and what of it, and that's fine. We can just leave it at, or what of it is like ordinal and numeric, and what of it is categories, and you have to assign some number to it, and what kind of a number, you know, is it ordinal or not for this here. So again, the pet ID is just a number. We can just leave that there. So we're actually going to largely ignore that. The type, this is a category, dog, cat, ferret, and this is what we're going to predict from this. So how would you classify this data? Well, actually, we're predicting how long it's going to take for this to be adopted. So how would you encode the type? Is this a ferret or a dog or a hamster? How would you encode that here, the type? Is it an ordinal number, or would you have to use our one-hot encodings? Is there an order to this or not? So like, to me, maturity size, small, medium, large, extra large, there's an ordering to that. Small, medium, large, extra large is, we say those in order from size there. But type, I wouldn't say that is. There isn't, I mean, I wouldn't say there's an ordering where hamster is more like iguana than dog is to cat or something like that. So yeah, you just have to go through and note those values here. We're actually going to be looking at that, I think, in next unit or the unit after that. I'm not 100% sure it made the cut because I'm cutting a lot of things out of this so we can get to large language models and some of the newest stuff in AI quicker. So. So again, for today, the learning practice, you just have to do this write-up here for this and do that and submit that. And again, and your copy of this decision tree. Again, right now, there's not a whole lot of changes in these notebooks. I'd like you to submit a copy of it, but later on, there'll be more chances for you to make modifications and change things at the notebook and run things there that we'll want to see. So that's why I like you to turn them both in just because later on, right now, I'm just basically grading your write-up. Now, again, for the project, if you're doing the classification project, again, you'll be comparing support vector machines, decision trees, random forest, XG boosting. Here will be create the models are here. You'll run the data through it and compare for this. Now, one thing that we do look at in this project is this bonus challenge of automating search. You might be thinking, Tom, why did isn't there a better way? Why did I try, all these combinations of neighbors or these problems? a linear search with this C parameter, a radial bias search with this parameter, all this. And, is there a better way? Can I just write a program to do this? And obviously you can. So there are nice, simple models that'll do a bunch of testing for you. You can just create what is called a grid here. So I can say the C parameter, I'm going to try these values, list a whole bunch of values. And then the kernel, I'm going to try these values here. And then we're going to do a grid search with this model, with these parameters. It will then try out every combination of those parameters. So here's running through all the different parameters, and telling you the score on every one there. And it'll then tell you the best set of parameters for your data set. And in this case, it's coming in with a C of 1.25 and a kernel RBF, and that's the best result for it. So there are ways of automating this parameter. We call these like meta parameters here. And so you can, rather than manually just trying out different ones, you can just have the computer try out a whole bunch of combinations and tell you what's the best combination. So the bonus challenge in the project shows you how to do that in case you're interested. The other thing that's a little different, again, with the bonus challenge is the data. You can select certain columns from all the 30 cancer ones, or you can just use all of them. So you've got to kind of experiment and say what you think is the best idea there. And the last thing we asked about is bias in this data. In the iris flower data, I don't know if there's any real bias. I think that's pretty straightforward, but let's just talk about bias like in cancer data here. This comes from the University of Wisconsin, Madison. And Wisconsin, as far as like racial background, age, that sort of stuff, that'd be very similar, I would say, to Minnesota here. And one of the questions is that does that matter here? Does it matter that we're picking Midwest, a sample of Midwesterners here for our data here? And a lot, previous, before we'd say no, it's just, that doesn't matter. But I think today we have a much more sophisticated understanding of things like healthcare and facial recognition, stuff like that, where we're saying that it's important that the population reflect who we're using this on. So if we're creating a model and applying it nationwide or even worldwide, or just in a certain area, if we're training this population, we're going to bring it over and use it in, Sweden. Is that a good model? There are the people in Sweden in certain ways that are important to breast cancer different than the people in Wisconsin. And maybe not. Maybe Wisconsin is a good sample set for Sweden there. But that's something we have to consider for this. So that's what I want you to look at when you do that, is bias in this data. Okay, I'm going to stop talking and stop recording. If you have any questions, let me know as you go through this. Chat people, feel free to post questions to chat or just say them.